Okay, let me welcome Rodrigo Arouca, who's going to be telling us about topological edge and corner states in bismuth fractal nanostructures.
Okay, so thank you very much, Joe, and hi everyone. I'm Rodrigo Arouca. I'm just joined the Brazilian Center for Research in Physics, CBPF, as a faculty member a bit less than 2 months ago, and um I thought to talk. I first would like to thank the organizers for uh, both for invitation and also for organizing. I don't know exactly if the workshops are related, but I know that there's like some series of workshops that happen uh, consistently, and I think it's very important for the Brazilian community working with these topics. Especially for me, it was quite important. Like I participated in 2018 as a PhD student, and Diego mentioned the lib lattice, and I think he had in mind Cristiane, because actually we met during this conference. And it was, we already had sent some emails, but it was the time that actually we met. And she was presenting some very nice works on the simulation of the lib lattice together with experimental colleagues in Utrecht. Uh, Today I'm going to talk to you about this work that, it's a bit, then I went to her group, we started collaborating. And in the middle, when I spent 2 times there, and back then, Professor Jin Fong Jia entered in contact with Christiane, saying that he had some very interesting measurements to discuss with her. And basically, it is the story of what I'm going to show you today. And just to give credit to who is due, the measurements were done by Chen Liu, that was at the time a PhD student in the group, now she's a faculty. Uh, and Christiane and I, we supervised Robert, that was our master student at the time, and together with Lumen, we did the theory for this work. So it's a bit, the main idea of this work is to kind of show that if you put bismuth on top of indium timonide, you generate some kind of Selmford fractals. And this fractal seems to be topological. So I thought it was an interesting topic to present at this conference, because it was something that is a kind of frontier in quantum materials. Bismuth, here we are looking at bismuth in low temperatures, looking at topological states. And it's a bit of a topic that I think is very interesting. It's not so well explored. I think fractalities in this context that I'm going to show. So I thought it was something interesting to show to you. So I know it's Friday, it's Friday afternoon, everyone's very tired after a lot of very nice talks. So I hope that I can at least show you these results, motivate a bit what fractals are nice, and that maybe put you to work, to think a bit on exactly if it's something that could be interesting to work with. So as probably you'll see in the program, at the time that this paper was published, I was in Uppsala. I just moved it recently back to Brazil. And I was funded at the time for the Knut Annelies Wallenberg Foundation. So we're talking about fractals, so what's a fractal? So I like to talk about this in a way that, I just construct a fractal together with everyone. So I can just start with a boring triangle that has some area A0, some perimeter P0, and I start to drill holes on it. So then, for instance, if I put this hole here in the middle, I make a triforce for the ones that like Zelda. And then, like, you can see that the area of the triangle diminishes a bit while the perimeter increases. I can do it again. So now the area decreases more, the perimeter increases a bit more. And if I'm very patient and I do it this infinite number of times, I arrive in this lattice or like mathematical structure here, called Sierpinski triangle. I'm sorry someone speaks Polish in the audience, but I don't know how to pronounce this properly. But what's very interesting here is that you see that by doing this process in an interactive way, you end up with some structure that has zero area and there's a very large perimeter. So it's something very interesting. This is not a property in general of fractals, but a lot of them has a no-integer dimension. So if you look on how this will grow, as you double the linear dimensions of them, you see that grows. It grows with 3, the number of sites that you have basically in this lattice. So if you define the Hausdorff dimension by how basically number of sides growing with this linear dimension, it will be something that is no integer. And I think the most defining property of the fractal that make it very interesting self-similarity. So this video never plays. I was actually very hopeful because I was playing upstairs. But basically the point is that if you have this true fractal, that's the limit of making this process over and over again. If you zoom in into structure, you have a self-similar structure. So basically you see the same pattern repeating over and over again. So it's the idea of like some kind of scaling variance that appears here. So fractals are, I mean, probably you heard of fractals before, and both because I think they are very nice, also they are very present in nature, especially because, as I was discussing, you have this kind of ratio between perimeter and area that's a bit unusual to what you are used to, right? So I think probably the one that everyone saw was this Romanesco broccoli that has this kind of similar structures. But also, if you think in terms of science, I mean, they are everywhere. I mean, at this conference, you heard multifractality many times before, also dynamical fractals. And this also happens, for instance, I just collect some examples that I like. So, for instance, there is this very nice science paper. The first author is Bruno Mota, is a physicist in the Federal University of Rio de Janeiro. He works a lot with biological systems, and together with Suzano Herculano, they show that basically if you look at folding of neurons, it follows a kind of fractal structure. So it's very interesting because the same way that you have, if you have folding of paper, it's related to how basically the number of neurons should grow there. And I mean, this community, I think I don't need to explain much, but also if you look at critical properties, so for instance here, if you look at the metal state and transition vanadium oxide, there is this very nice PRL from Erika Carlson's group that show, for instance, that you also have multifractal properties. So there is this fractal properties and kind of some relations that have this kind of self-similarity in many areas of like life in general, or like nature. Also in physics is also quite common. But now if you think about materials that form this kind of fractal structure by themselves, like in terms of lattice, is not very common. I mean, you know that usually these crystals tend to be periodic and have a nice repeating pattern, and fractal does not have this kind of structure. And actually, Cristiani also, in his work with Daniel von Mackelberg group and Enigma Zwart group in Utrecht, they actually build a fractal using basically like a surface of copper that basically behaves like a kind of free electron grass, and then you can attach some CO molecules on it, and basically they act like some kind of potential barrier. So basically, if you cannot find a fractal so easily, you can just build one by yourself. And the way that they did it is basically to kind of shape the regions in the lattice where the electrons will not sit, because basically you have this repulsive potential. And if you look at the experiments and the theory, both using tidal binding and Muffington calculation, that basically is doing this in terms of Schrödinger equation, you see that, I mean, they have this kind of fractal shapes. So of course, it's not a true fractal. I mean, it's if you want to be very snarky about this, you would have a triangle with holes. But I mean, it's not something that's like it's not infinite dimensional. You don't have an infinite number. But there's still a lot of very interesting properties. So for instance, if you look at if you look at this, by the way, these are SMN measurements. So if you look at this kind of the density of states and see how it is spreading, like if basically you have something called a box counting, that you count the distribution of this density of states with some radius. It has a property that you expect from a system with no integer dimension. So even if you are in a finite generation, you still see a lot of the features that expect from a fractal. So so this paper, I think, was quite important. For instance, was the cover of Nature Physics. And as I mentioned, I think was something that also a bit later, when the people in Jingfeng group, especially Chen Liu, were doing measurements in this kind of material. I think was the reason probably they contact Cristiani to discuss a bit, because basically the measurements that they were doing is that they were growing bismuth films on top of indium timonide, and they saw that naturally you would form, I don't know if you can see well, but basically I have some better images later with focus a bit on some of the structures. But basically, you see that you have a very homogeneous system with a lot of fractals being formed there. So as again, it's not a true fractal, it's like approximation of a fractal. And the reason that this happens, I think, is quite interesting. Unfortunately, I'm not a very big specialist in strain, but it seems that you have such a large mismatch between this indium timonide and bismuth that the system to actually basically to release this kind of tension that creates this strain, it forms this kind of structures here that you can call these strain solitones or also this kind of fractal shapes. Something that, so this was published in this PRL, but something that's not there, because actually this was in collaboration with some groups doing ab initio calculations that actually explain why this system formed and doing this analysis on the structure. But something that was not there was basically the spectroscopy data that they also acquire with STM. And then here, if you focus on some of these bismuth flakes, you have like formation very close to the Fermi energy. You have states that are localized either at the corners of these flakes or the edges, either the external or internal one here. So basically the motivation that, basically they want to talk to Cristiani and also that we start to become involved in this work was, well, if these states are topological, because, these are kind of look like a lot like edge and corner states. And I think this is something that if you know a bit about bismuth, it's not very surprising. So I actually have something to show you. So I don't know if you ever saw, but this is a bismuth crystal. So bismuth is a kind of amazing material. So it has this kind of iron throne shape. So I'm probably citing Joe for the joke, but you see that it has this kind of very nice structure, and it forms also with these nice colors. I don't know if you're bored with my talk, you can take a look at this. But also is a very heavy material with a very large spin-opt coupling. So for instance, if you just look at this bismuthine, that's a kind of cousin of graphene. So it's a it's a monolayer of bismuth. If you put on silicon carbide, it's a candidate for quantum spin Hall insulator with a very high gap. And also, even if you take elemental bismuth and you have it in the correct shape, it's also, for instance, one of the first high-order system that show high-order topology. So this was, if you think about the paper by Ben Alcazar, Benevig, and Hughes, for instance, was a year after. So basically, this is the question that we want to answer. I want to answer in this talk. And just before we enter into that, I'll try to motivate why this question is interesting at all. So, okay, so we have fractals and maybe their topology, and then why should I care? I should care because I'm in the paper, but why you should care like we're here on a Friday afternoon? And I think the reason that is an interesting question is that, this is a bit more technical maybe, but when you think about this topological phase of matter, usually you think about invariance in momentum space. You have no translation invariance, so then actually you need to use some local markers. But this, I think, is not a fundamental point. Something that I think is more interesting is because, since you have this kind of many length scales in the system, actually you're gonna have also this kind of multifractal spectrum. And because of this multifractal spectrum, actually you have many edge and corner states at different energies, and they'll be localized in different parts of your system. So I think this is something that is quite interesting because you have this topology at many different energies, also many different feelings. There is also this point, and I think this is not so relevant for what I'm discussing today, but I think for me is a very interesting prospect for the future, that basically, when you're really thinking of a true fractal, you're going to this a limit where you have the system between dimensions, right? So, of course, as I said, here we have a system in 2D, and then you're putting holes on it to increase the number of edges. But if you actually have a limit that you're going to the true fractal regime, you're basically going more to a 1D system, right? You just have perimeter. So how you fit here in this Landau classification? So I think this is an interesting point. So I think there's been some progress understanding this area, and I think this is basically the thing that motivates most of the work on that. So I'm gonna discuss some examples that I think are nice and show some of these properties. But also I'm gonna try to cite properly the main people that work on the topic. So for instance, let's think about a lattice version of a quantum Hall effect. You have a Hofstadter model. And then you, for instance, have it make it in different shapes here. So you basically have different ways to create this fractal. I'll not enter into detail on the notation here. But basically here what you do is that you're going to put this in a Hall bar and you're going to see the Hall resistance. So if you look at this, I mean, basically the results are not very different from what's expected from a quantum usual offset model. You have this offset butterflies, and basically you have quantized plateaus here. Here you're thinking that you have inverse of resistance here. So basically this is related directly to this kind of chair number. So here in this work, they compute this chair number using the Kita formula, but you can also use REST a way to do this, and the results are very similar. So basically what I'm trying to show here is that, first is that, I mean, in principle, what this figure is showing basically is going from creating more holes here in this kind of big rectangle. And then in some sense, I mean, you still preserve this topology, but seems that in some sense you're destroying it a bit, because I think really you're going from this 2D to 1D limit. But there are some things that are interesting, because in this paper, I think they do not look at the localization of the states. If you see that they are localizing a lot of different parts of your system. So for instance, this is another work that I like that look a bit on this high-order topology. So for those that have seen it before, they are looking at the Benel-Kazaf-Benevik-Hughes model. So it's a model that was the first model to display high-order topology. It is not very important. The important point here is that you have these states are localized in corners. And then what's interesting is that if you look at if you make this in a fractal lattice and you look at it, you see that you have this kind of states that appears in different energies. So instead of being something just as 0, you have states in multiple energies, and as I mentioned, they're localized in different parts of your system. So this kind of, if you just look at the environment, like this global environment, you lose a bit this part of the system. The last thing that we're going to talk about in a bit of this introduction is that actually, and this I think is a more interesting perspective, if you look at the topology of this fractal, I mean, the fractal itself can introduce you some topology. So if you just take a system, like you take a Kagome lattice that will have been heard a lot, and then if you don't have any kind of, if you just have uniform hopping, don't have anything, don't have magnetic field, don't have any kind of interaction, don't have much interesting things going on. But now if you put this, like it's this kind of fractal with this Kagome kind of structure, it's very interesting because this is actually kind of, this is a bit complicated analysis. I really recommend you to take the PRL if you're interested. But this kind of, there is a way that you can show that the physics of this problem is very similar to the one of this Kagome lattice with dimerization. So basically, you introduce the fact that you have this kind of multifractal property of your system, introduce some kind of new physics in there. So, and just to show also that, I mean, this kind of thing, so basically they show, in this paper, they show, including two of my collaborators, they show that you start to create this kind of states. And what's interesting also is that you can have states that don't have crystalline, like the usual crystalline symmetries that you have in two different, you have system with C5 symmetry. So it's also interesting if you think about crystalline topology, that you can actually have some kind of phase that you don't get in a regular crystal. So I mean, it's the same for quasi-crystals, but here this also happens. So this is trying to be, as I said, to be a bit fair on what people have been doing. So I think there have been, since 2018, more or less, has been some kind of works in the field in terms of the theory. I mean, maybe there's works that are a bit older than that. I'm sorry if someone knows some work and I'm omitting it, I'm happy to add more citations here, and I'm sorry if the case. Especially, I think, when you think, so this, I mean, not going to throw to the list, this I just put here someone to take a picture. But also, for instance, in this direction also of connecting disorder with multifractality, I imagine this is like, should have much more citations here than I have. But I mean, there are other groups like Bitton-Roy group and a Nielsen group in Denmark that work very hard on that, and this I think is just a way to do a bit just of that. But this, I've been told, most of these works were done with theory, and I think now we start to see some experiments. So, for instance, there's a science paper on 2022, they actually look at this kind of waveguide systems, and basically using some kind of twisting of these waveguides, they create basically a Haldane model. And then you see, I think maybe it's not very clear here, but you actually see edge states and you see all the physics of the Haldane model. And also, I mean, this kind of high-order topological insulators that I mentioned you also see in this kind of acoustic platforms. But these are metamaterials, so I think it's quite interesting if you go to this bismuth platforms, because actually you get, in principle, a candidate for having a real material that presents this kind of behavior. And I mean, something is not something that you are designing, something that just happens naturally in the lab. So this is a bit a better like representation of what's going on. So you see, this is the kind of STM images that Chen-Liu measure, basically. So you see that you have many different flakes, quite homogeneous systems with a lot of this kind of fractal-like structures. And basically, we're gonna look at some structure like this that looks like a second-generation Sierpinski triangle. So because of the size of the system, we cannot resolve actually if it's second or third generation, but does not matter so much for the properties that I'm gonna show today. So basically, our main point was to try to see if we can explain the system using some two theoretical methods that we're going to show, basically a muffin-tin calculation in a tight binding model. And if we can actually reproduce these features that they are localized in the edges and the corners, and if actually we can match the kind of appearance of them here. So the muffin-tin part was done by Robert. So basically, it's a, I mean, it is a very simple, it's probably the simplest Hamiltonian that you saw in this conference. So you have kinetic energies and intrinsic spin-optic coupling and a Rashba term. You have some potential that basically just confine your electrons. So basically, we are assuming that because this system is basically a two-D lattice with a very strong spin-optic coupling, that if we confine them in this geometry and add this spin-optic coupling, basically we hope that we can describe this system. So basically, we try to having a potential landscape that mimics the kind of flake that I show you in the last slide. And then this is actually the way that we do it. So these actually are the regions that I was showing. You have these potential landscapes. We are using Gaussians here just because we have derivatives, so it is a bit more smooth. And then basically we're discretizing this in a lattice, in a grid. And we are solving this and obtaining the wave functions that basically give you the density of states. A similar approach that was done by Lumen was to use a tight binding calculation here. So we basically assume that we have this kind of flake. Since bismuth is the main protagonist here, we use as a base some ab initio calculation that show that the relevant orbitals here, the S and Px and Py, and we did these 6 orbitals. Three orbital tight binding model here with this kind of hybridization between these orbitals and also the Rashba to account for the fact that we have a substrate. So this is the comparison between what they had in the experiments and the two simulations. So this is the flake that they focus on. We have other measurements that and also the theory that is more on the we have like a 50-page submat with a lot of details there. This is the muffin-tin calculation, so this is showing more or less the potential landscape. And then we have this kind of tight binding lattice here, and then we try to show the results. So something here that's a bit different between theory and experiments is that in theory we try to set the peak of the density of state to be something constant, while in the experiment usually it's something that is done in the sample. So for instance here we don't see anything for tight binding, but it's just because I'm gonna show maybe later some figures where actually we take the maximum value for each energy to show actually that you have more features that are a bit similar. But since in theory, in principle, you can control the peak of the local density of states, we just kept it fixed. So just to show here that if you are far below the Fermi level, you basically have this kind of more bulk states. And then, it's interesting because you can really see that it has a bit of the properties of the fractal lattice. So, for instance, you can see here that you have this kind of node in the place that you have this kind of hole that you see here. And this is more or less close to what we actually did in the simulations. And it's interesting because I think this part here maybe is not so similar, but really when you go closer to the topological states, you can see that you have very clear these corner states, and you have these edge states at both the external and internal ledges. And this is something that because of time I'm not showing to you, but also we checked that if you turn off spin-optic coupling, you don't have this kind of features, and so it's is also something that, we are really kind of confident that these are the kind of ingredients that we need. And just to show you here, like this is what I mentioned before, if you have like a scale-free tight binding model, it looks a bit closer to the muffin tin simulations and also the other things. So in my title, the first word was topological. So I'm not showing you any variants, and so why I'm calling this topological at all. So I think this was something that we should have done, but there's some reasons that we do not do it. The first one is that, as I mentioned before, bismuth by itself, if you just have this kind of triangular shape, is close to at least a quantum spin Hall state. So, in some sense, we kind of expected it to be. The state should be topological. Also, in terms of simulation, at least we have a bit more to say, because you just have this state when you have this kind of high, very strong spin-opt coupling. Also, in simulations, we can play a bit with the states. So, for instance, as I mentioned before, the system was very homogeneous. So, we can actually play a bit with disorder. We kind of imagine that, the states will still be there because it was homogeneous. But, we did many kind of different disorders, so we glued this kind of things together to look a bit more like the experiments. We have some disorders in the height of the potentials here. We actually changed the position of these potentials. I'm not showing here the worst case, but for instance, you can go up to like 20% of disorder and we still see this kind of corner state, and edge state. So it seems like something that's quite robust, at least. If it's not topological, at least, at least in terms of simulation, is quite robust. So this is more or less what I wanted to say in terms of the physics. So this, I'm doing a summary of the main results and also some things that I think are interesting for the future. But before doing that, I just want to, just to say that, it is also in accordance with other results, for instance, for bismuth, also even the amorphous bismuth. So it is also work from people from Brazil. So before going to the conclusion, also trying to give some outlook and looking for your questions. I just want to do some shameless advertisement. So as I said, I just joined Rio as a faculty member, so I'm really looking forward to have students. And I just, if you're interested in this, I just want to say a bit on the things that I work with. I work with I work with quantum matter in general, but in principle, my background is superconductivity, but also I'm working more on topology recently, and especially this kind of interface between topology and open systems. So, and I'm just giving you a bit of a menu of things that I'm doing at the moment, and maybe if some of these things are interesting for you, maybe drop me an email or chat with me, and we see if we can work together. So, for instance, now we are finishing a project that we are looking at a Rashba nanowire and coupling to cavity. Look like a cavity. It's quite interesting because you have an interacting system and you have some properties that are a bit different from what you're expecting it. And also, if you have a Majorana fermion or a regular fermion, they behave quite differently. I have been working for some time in exons in twisted TMDs, and I hope in the next weeks we have some very interesting things in archives, so keep an eye on. So it's something also that I'm quite interested in and I should focus more on in the future. There are some works that I have been doing for the last years on thermodynamics on no-emission systems, especially now we are trying to connect the critical properties of no-emission systems at zero temperature with the properties at finite temperature. So I thought it was something a bit trivial, but then I started collaborating with Pasquale Calabrese on it, and we're having a hard time, so I think it's really like a very interesting topic. I'm also looking a bit on this superconductivity with magnetic adatom, especially also thinking in terms of these fractals. And I'm also working a bit with the Keldysh formalism for like this system, especially look at anomalies. And by the way, a kind of project I'm very interested at, but I'm not sure if it's very difficult, but is also to try to understand this topology and these fractals from a more fundamental point of view, look, for instance, at anomalies. But I think because of this interplay between with the self-similarity, I think it's something that at the same time is quite interesting, quite hard, but I'm still very interested to look at that. So just to show that, it's not only Barcelona or San Sebastian that have nice beaches, so like CBPF is in a very nice position in Rio, between like Copacabana here, and also you have the Sugarloaf close by, so it's a very lovely place as well. You also have very nice colleagues like Tobias and Eduardo too. to be around you. So with that, I close the shameless advertisement. And basically, I just want to give you an overview of what I talked today. So basically, that if you have bismuth on indium timonide, they form the self-assembled fractal lattices. In principle, it seems that, I mean, the description of the system in terms of these 2D lattices with a very high spin orbit coupling, and these states that are protected against disorders is like seems to be a good description of them. Something that I think is really interesting because for me, I really see this work as something that opens a door, something that actually could be a bit more interesting. So, for instance, I really think it's nice to look at, at least in terms of theory, and hopefully experiment, but maybe this will be a bit more in the future, is to try to look more on this limit of the true fractalities where you're playing between the 2 dimensions. And especially in terms of experiments, I really would like to see and try to describe experiments that really address directly the topology. So this was something, unfortunately, like took some time for us to finish the calculation. So we had a bit of rush to have the paper out, but this I really think it should be something that should be done quickly to, I mean, really more directly see that we are talking about topological states. So with that, thank you very much for your attention and look for questions.
A nice talk. From my understanding, but perhaps I'm wrong, this kind of fractals that are constructed from a triangle are just one possibility to build a fractal.
Yes.
So why the nature, there is a reason behind a real material has, I mean, these features are particular from this kind of fractal or could be general, and why a real material will correspond to this particular kind of fractal, because it's not obvious for me.
No, yeah, I think I mean, for me, it's not obvious as well. So as I mentioned, I mean, a bit this formation of the fractal is something that is not something that I work with. I mean, I just look at the structure. I mean, in my understanding, the fact that, I mean, this is very close to the lattice that bismuth, if you just like a layer of bismuth, they'll create some lattice that's very close to this itself. And I mean, the fact that, I mean, you have, at least for this system, that you can grow bismuth on top of indium timonide, then, I mean, we'll favor to create these kinds of Sierpinski triangles because of this large mismatch. But, I mean, whether you can create other shapes and I mean, even like all the kind of fractals that, I mean, are a bit more complicated, like the ones that I showed a bit before, for me is unclear. I think it's really something to be asked, looking at this stability of these lattices and this kind of more, really model-looking structure. But yes, sorry, yeah.
Okay, did you try computing some Bolt indexes for these topological phases and actually verifying numerically?
Yeah, no, yeah, this is a good point. I mean, we start with this calculation, but as I mentioned, was something that just to have a good, I mean, this was something that I forgot to mention. I think you can use this one, because here, I mean, we're not doing ab initio here. So basically, we are trying to look at the parameter regime where actually you can describe well the system. So this itself took a bit of time. I mean, I'm showing you something maybe a bit too easy, but actually, like, we have a very big parameter range, and it took a bit of time, and we were like a bit rushed to publish. So, I mean, in the end, we decided to not go with the invariant, but there was later work where people computed bot indices or like these local chair markers. For instance, now I'm working with another invariant called the spectral localizer that works quite well also for this system. So I think there's, I mean, in principle, I mean, this kind of technical question, I think is quite, I mean, it's very easy to implement this kind of things.
Thanks for this really nice talk. So I was just wondering experimentally, what sets the scale of the structure? I mean, when you vary, is temperature, is energy? I mean, do you know?
Yeah.
I mean, how would be? I mean, is it possible to grow larger?
Yeah, this is actually the thing that they're working at right now, because the way that I understand, I mean, this was a bit of surprise for them that this structure formed, and the FT calculation so that these are related to like this strain relief mechanisms. And then now they are trying to play a bit with this kind of growth conditions, both temperature, also like the kind of Yeah, mainly temperature and also other experimental parameters to actually see if they can grow larger, if they can grow different shapes and other things like this. So this I think is like I'm not sure how which parameters enter in that, but the experimentalists are working on that right now.
I have. Oh, yeah.
So probably a more like thinking about the theoretical questions, like what would be an edge to a fractal? Because like every time you have these topological phases and things, you think about the edge states.
Mm-hmm.
And for example, if you have a 3D material, you have edge states living in a two-dimensional
Mhm.
surface. So like for a fractal, what would be an
Yeah,
edge?
So I mean, this I think is an interesting point when you really look at the true fractal, because I mean, in this fractal,
Yeah, the true fractal. The true
because
fractal.
because then there I think and this I think why it's an interesting question to look at this, because I think for me there is some points, because I mean there are some points that are universal in this kind of fractals that I'm describing, and the really mathematical ones. So that I mean, for instance, the fact that you have this kind of scale invariance, the only thing here that you have length scale, so basically like you don't go all the way. But there are other things like, for instance, what is a edge, whether it is really an edge state is an edge state, or it's just like a kind of more bulk state. I mean, I think it's really a good point. I think there you kind of lose this kind of things, because I mean, basically you kind of have this kind of you basically lose length scales, right? If you have self-similarity. So
Yeah, just thinking about, for example, the dimension of the
yeah.
of the fractal. Yeah.
Yeah.
Thank you.
Yeah, and I mean, just to say, I mean, this I think is clear, but I mean, here, of course, the edges are things in
Yeah,
the
thank
whole.
you.
Yeah.
Okay, I have a question. Okay, so at the edge of each of these voids in the triangles, right? I don't think the bismuth complete their bonds, right? Like they'll have one that's empty.
Mm-hmm.
I know you didn't look at any of the
Yeah,
those
it is.
details,
I'm not sure. Yeah.
but I mean, so in terms of a lot of the topology that you're talking about, you would expect the edge states to pile up there, but this would possibly be a source of very strong interactions too. Do you have any intuition for what?
Yeah, I think this is a very interesting point, and especially I think something that I did not mention these things is also that, I mean, in terms of interaction, I think also playing along dimensions is something interesting, right? Because I mean, 2D and 1D for interaction is quite different. So, and I'm not sure here if actually. So you're saying that that I mean, that the fact that you have this kind of free bonds there will have strong interactions at the edge of the system because of this.
It may.
Yeah, I'm not.
It depends on details. Usually.
Yeah, but why this would be the case?
So I mean, usually the electron sits between bonds in order to minimize the energy, but now you're going to be piling up electrons.
Mm-hmm.
on
Okay, I
sides,
see.
right?
Yeah, no, that's an interesting point, and I'd not thought about that. Yeah, yeah.
Anyone else? No. All right. With that, let's.
No, thanks.
Rodrigo.